Today we're going to look at a practical example of electromagnetic induction. That is, we're going to look at transformers.
You've probably seen little transformers like this in the back of your computer. 120 volts AC comes out of the wall socket. It has to be stepped down to a lower voltage so that it can drive different elements within your computer. And in my neighborhood, there's a whole bunch of these steel green boxes on the boulevards. And those are transformers. That household electricity also needs to be stepped up in some cases and stepped down in other cases. And large transformers are used to do that. If you want to build a transformer, it has a very simple structure. You'd start with what's called an iron core. Just a piece of iron in a shape approximately like so. So this is our iron core. If you look closely, the iron would be what we call laminated. It'll be cut into thin sheets. So there's a whole bunch of thin sheets stuck together to make this iron core. And that greatly increases the efficiency of the transformer. We'll talk more about efficiency later. Then what we do is we'd wrap a piece of wire around the core. So let's 1, 2, 3, 4. So let's say I put 4 turns of wire around one side of the iron core. I'm going to call this side, really the input side, I call that the primary. And then on this primary side, that's where I'd have a AC signal. It's got to be an AC signal. That would be connected to the ends of the wire that turns around the core. And I do pretty much the same thing on the other side of the transformer. So I'd bring in a wire and I'd wrap it around. But I'm going to wrap it around a different number of times. So the last one was 4 times around. I'm going to try to make this 8 times. Although I'm running out of space. 5, 6, 7, and there's an 8th. So now I've got 2 ends here. That's the output, or what we call the secondary in transformer language. And then my load will be attached. The thing I want to run will be attached to this side. So I'm going to represent that as a resistor, which I call the load. So the number of turns around the primary, we call that NP. So in this case here, we'd have NP equal to 4. And the number of turns around the secondary, we call that NS. And in this case, we've got NS being twice as many. Being twice as many as NP. So this would be what we call a step-up transformer. Meaning, let's say my input, my primary voltage here is 10 volts AC. Then because I have twice as many turns here, I'd get a voltage. I put a voltmeter around the load. I would find that that voltage would come out to be 20 volts AC. So because I stepped up the number of turns by double, I double the voltage coming out. And that's what transformers do. They step up and step down voltage. So transformers step up and step down AC voltage. Transformers have this important role in history because there was a great battle that went on between AC and DC electricity. Tesla wanted household electricity to be AC, and Edison wanted household electricity to be DC. However, transformers, which are this highly effective, efficient way of stepping up and stepping down voltages, only work on AC. And there was nothing comparable back at that time for stepping up and stepping down DC. Nowadays we have some good methods of doing that, and perhaps today DC would be a better choice. But we're stuck with AC, thanks in part to the transformer. Let's see how a transformer works. So we've got our transformer here. We're going to just take a little household battery and connect it up to the primary. And let's throw in a switch. So as soon as we throw that switch, we're going to generate a current in that coil, and this will become like a little electromagnet. So we'd have a north end to our electromagnet and a south end, and we get field lines. And because we've got an iron core here, the field lines wouldn't spread out. They would stay inside the iron core, and they'd go around this second loop and come back to the south side of the magnet. So we'd have these magnetic field lines circling inside of our iron core. Now when we first throw the switch, the magnetic field would increase, and we get an increase in flux through this second coil, and we get a little pulse of voltage there. But if we just closed our switch, the magnetic field would become steady. We'd have a steady current, and we get a steady magnetic field through this coil. But then there wouldn't be any change in the flux, and so that wouldn't produce anything else. If we decided we were going to close our switch and open our switch and close our switch and open our switch and close it and open it, then of course the flux would change. You'd get kind of pulses up and down as you opened and closed the switch, something like that. So, which is to say you can't use DC circuitry unless you decide you're going to flip your switch along. What's much better is to have an AC supply here at the primary, because what that's going to do is reverse the current in the coil 60 times every second. So if this is like a little electromagnet, it would be north and south. But 1/60th of a second later, it would be south and north. So our magnetic field lines would circle in one direction for about a 60th of a second, and then they would circle in the other direction for a 60th of a second, and that would go back and forth, back and forth, back and forth 60 times per second. So now we've got a changing flux through this secondary coil, and our output is going to be a voltage that goes up and down, just like the AC signal going in. The difference is going to be, because we have twice as many turns here, the peak voltage being produced will be twice as big at the output or the secondary than it is here at the primary. So AC causes the flux at the secondary to be constantly changing, producing an output AC signal. We said earlier that if I double the number of turns on the secondary, that I'll get double the voltage coming out of the secondary as on the primary. We'd like to show that that's true. So here's my secondary side, and here's my primary side. I'm going to start with the secondary side first. We know there's going to be this flux being produced, this magnetic flux. Magnetic field lines is what I'm drawing here. And that's going to be oscillating back and forth 60 times every second. So we've got this changing flux, and it's going through both of these loops, not just one. And it would be the same flux through both of those sets of coils. Here at the secondary side, it's going through the number of turns that are on the secondary. And by Faraday's law, that has to be equal to this output voltage at the secondary voltage. Faraday's law would include a negative sign, but I'm really not interested in the direction here, so I'm just going to work in terms of magnitudes. So this is what I've got at the secondary side. Now let's go over here to the primary side. This set of coils here has exactly the same flux going through it. The flux is going throughout the whole core. So we've got the same rate of change of flux. If I multiply that by the number of turns in the primary this time, so we've got a certain number of turns here at the primary, then I should get, by Faraday's law, some EMF that's produced. In fact, that EMF is going to oppose, by Lenz's law, it's going to oppose whatever this primary voltage is doing. It opposes those changes. And if we make a little assumption, that's a pretty good assumption. We assume R equals 0 in the coil. And we have this thing called Kirchhoff's voltage law, which says that the sum of the voltage drops around a loop is 0. And being as we have no resistance, there's no voltage drop across the resistor, which means that this Vp, this primary voltage, is going to have to be equal to, but opposite in direction, to the EMF caused by the changing flux through the loop. That is to say, if I take that Vp and add it to that induced EMF, I've got to get 0, which means these are the same size but opposite in direction. And if I'm just working in magnitudes, I can then say that Vp must be equal to Np delta phi over delta t. And if I set the two fluxes to be equal in these equations, I get that Vp all over Np is got to equal Vs over Ns. Or I could write that as Vp all over Vs equals Np all over Ns. And that's it. That's our proportional relationship. If the number of turns on the primary is twice as big as the number of turns on the secondary, then that primary voltage is going to have to be twice as big as the secondary voltage. Now you're probably thinking these transformers should solve the world's energy needs, because all we need to do is step up voltage and we have more energy. Well, voltage isn't quite energy. Remember that voltage is joules per coulomb. It's energy per charge. And that means the energy will be equal to the voltage times the charge. So if we step up the voltage, we're going to have to step down the amount of charge if we're going to have the same amount of energy in as out, if we don't violate the law of conservation of energy. Or the way we usually think of it is that power, the rate of flow of energy, will be equal to voltage times the rate of flow of charge or current. So in the very best case scenario, power in, power at the primary, will equal power out, power at the secondary. And once again, if we try to crank up that voltage, we do so by getting proportionally less current. And you can see that if I write that power in equals power out, so if we have an ideal transformer, that would be equal to the current at the primary times the voltage at the primary. And on the output side, we'd have the current at the secondary times the voltage at the secondary. Now if I put the voltages on the left-hand side, I get that ratio of voltages equal to the ratio of the currents. But the currents are the other way around. They're the secondary divided by the primary current. So as I crank up the voltage, I get proportionally less current. And keep in mind, both of those will be equal to the number of turns at the primary divided by the number of turns at the secondary. So unfortunately, we don't get something for nothing. Let's try a problem. Pause the video, try the question, come back for the answer. So we've got primary number of turns of 200 and a secondary number of turns of 800. So we're increasing the number of turns. That means it's a step up transformer. B, the ratio of the secondary voltage to the primary voltage, Vs over Vp, has to be equal to Ns over Np, which is what, 800 all over 200, or 4 times as much. Part C, what will be the frequency of the secondary if the input frequency is 60 Hertz? Well, it's going to be 60 Hertz as well. It's the same frequency everywhere. The frequency doesn't change. Here's a second example involving a portable radio. Pause the video, try the question, come back for the answer. Let's start by writing down the quantities that were given in this problem and the quantities we need to find out. So this 120 volts AC, that's our primary, our input voltage. 9 volts, that's our output or secondary voltage. 30 turns, that would be the secondary number of turns. We don't know the primary number of turns. We're going to try to find that out. And we've also got that the radio draws 400 milliamps. That would be the secondary current. 400 milliamps. And we'd like to know what the primary current must be. So for part A, the ratio of the voltages primary to secondary is equal to the ratio of the number of turns primary to secondary. So we've got 120 over 9 equal to the number of turns in the primary over 30. Solve for n primary. You should get 400 turns. Part B, now we're looking for the current in the primary. We're looking for IP. So once again, we can use that ratio of the voltages will equal kind of the inverse of the ratio of the currents. It's going to be I secondary over I primary. So our primary was 120, secondary current was 400, that's in milliamps. So we can solve for the primary current, and that's going to be an answer in milliamps. Solve for IP, and you should get an answer there of 30 milliamps. And then finally part C, this time we're looking for the power transformed. For the power, we want to multiply a voltage times a current, so we could do that for the primary case, V primary times I primary. Or as well, we could do it for the secondary case, V secondary times I secondary. Either way, you're going to get the same answer. Let's do it with the primaries here. V primary was 120 volts. I primary was this 30 milliamps. We've got to convert here to amps to use SI units and get power in watts. So that would be 0.030 amperes. Multiply that out, you should get 3.6 watts of power. And you should get the exact same answer if you use V secondary times I secondary. So we said that transformers are this highly efficient way of stepping up and stepping down voltage. Well, how efficient are they? It turns out it ranges between about 85% and about 99.75%. The lower values would be for the smaller transformers. You get higher values for the efficiency with the larger transformers. The big ones that are stepping up and stepping down the electricity passing through the hydro wires. What are the causes of inefficiency? Well, there's lots of them. One of them would be the fact that any piece of wire has some resistance in it. So if you have a long coil of wire, it's going to have some significant resistance. So one problem is simply the resistance of the coils themselves. Another problem is what we call eddy currents. Whenever you have a changing flux through a metal, you'll produce these eddy currents. And these are largely eliminated by using the lamination, using the laminated sheets of iron. That's what they're for. A third effect is because some of the magnetic field leaks off into the air. The permeability of iron is much, much higher than air, so most of the magnetic field stays in the iron, but some of it leaks off. So some magnetic field leaks into the surrounding air. A fourth cause of losses is called hysteresis. And that has to do with the magnetic field changing direction 60 times per second. Every time it changes direction, it loses a little bit of energy due to what's called hysteresis. A fifth cause would be vibration. I know some of the transformers in our lab, they vibrate when you use them. Remember that current-carrying wires have forces between them, and those forces can cause vibrations, and those vibrations are energy losses. And there's a sixth effect called magnetostriction. That has to do with the changing flux inside that magnetic core causes the magnetic core to expand and contract very slightly, and that leads to losses as well. So in a good transformer, all 6 of these effects are reduced to an absolute minimum.
Final example involving efficiency of a transformer. Pause the video, try the question, and come back for the answer. So we want to work out the efficiency. That has to equal the output power over the input power, which we now call the secondary power divided by the primary power. And of course, power is equal to voltage times current. So we could write this as Vs Is all over the Vp Ip. Secondary power over primary power. We know that Np divided by Ns is equal to 15, and that has to equal Vp over Vs. And I can see a Vs over Vp here. So I could write that Vs over Vp is equal to 1 over 15, and put that in, 1 over 15. And then of course I've got my Is and Ip. I'm given those values. Primary current was 3, and the secondary current was 43. I don't have to worry about the units for the current as long as they're the same units, because it's really about the ratio of currents here. So I get an answer of 43 over 45, which I can convert to a percentage, and I get about 96%. So our transformer is 96% efficient in this instance. An important note here, Np all over Ns is always equal to Vp over Vs. That's always true. But that does not always equal Is over Ip. That's only true if you're at 100% efficiency. So don't assume Np over Ns is equal to Is over Ip in all circumstances.
So let's summarize the big ideas. I'm going to start just by writing down that key equation, that voltage ratio is equal to the number of turns ratio, but the current ratio will go in the opposite way. So if the others are primary over secondary, this goes as secondary over primary. This is really only true if you have an ideal transformer. But we know that real transformers aren't more efficient than about 99.75%. So real transformers are between 85 and 99.7% efficient.
So please take the time to like videos, to make comments, to ask questions, become a subscriber, sign up for notifications, become a member or a Patreon.
And that's all for today, folks. Thank you very much.